You get the live show anyway. That's much better, right? Sure. So any questions or things that you want to hear about specifically before we dive back into the world of time invariant predictors?
Did you say there was like a code for R, for like
all the stuff?
Not on your website, but like
it exists, yes.
Okay.
Somewhere on GitHub is code that was developed by a graduate student at the University of Victoria when this material was used in their graduate course. And it's somewhere buried in my email, and I keep meaning to put it on the webpage. But if you'd like to see the R code, please send me an email to remind me, and I'll put it up on that main webpage if I can find it. I haven't verified it or vetted it, but so take it as it were. But yes, it does exist somewhere. Whether or not I will eventually acquiesce and put R code on piles of variants, I haven't decided. I'm not an R user. I refuse to drink the Kool-Aid. But the rest of the world is moving that way, so I can only hold out for so long. Yeah, I believe you get what you pay for. That's the problem with statistical software. So it makes me nervous that some guy in his basement can make up a new R package and it becomes a thing without any level of oversight or quality control. It makes me very nervous that that can happen. So, but that's a whole separate question. For LME4, yes, that should be very lovely and stable and reliable for you. All right, other questions? All right. So we were talking about adding time invariant predictors, level 2 things, people things you've only measured once. And so I wanted to just briefly touch on ideas of model building and the way that I typically approach this. So when you look at textbook examples, they rarely have more than 1 or 2 predictors at a time. And in reality, you may have a whole host of predictors that you're interested in. And so the question becomes, what do I do first? So picking up on slide 34 within lecture 3 here, my strategy is usually to estimate at the beginning point separate models for each time invariant predictor so that I can see what its effects are without controlling for anything else. So an example, what we're going to look at is our random quadratic model of change in response time and a predictor of age at baseline. I can fit effects of age by linear time, and age by quadratic time so that I can see, does age matter? Just answer that question. Then, after I figure out what matters in a bivariate sense, just looking at one predictor and one outcome, I can combine the predictors together in whatever logical combination makes sense or answers my questions, and I can answer a different question, does age still matter after controlling for my other predictors? So for instance, we're going to examine a predictor of abstract reasoning, and if I have a model that has both of these in there, I would want to know, is age still significant after controlling for reasoning? So if age were to be non-significant in this combined model, it could have been because age never mattered or because it doesn't matter anymore. And those are two different things. And so for that reason, I usually start just by looking at one predictor at a time. That can be labor intensive unless you can figure out a way to trick your software into making it do all combinations. And so I have figured that out. An easy thing to do all of these combinations in one model is to make use of stacked data structure. So you know how we talked about stacking, the idea of going from a wide to a long where each row is for one occasion? Well, you can do that same thing again where you create a column for a generic label of predictor. And in one row of data, you make predictor A, next row of data, predictor B, predictor C, and so on. In ProcMixed, in SPSS, and other places, you can tell it to run your model by some other variable. You can tell it to go by predictor, and then it will spit out the same model for every single unique predictor that you put in that stacked data set. You can go one step further if you have lots and lots of outcomes to do this for, and you can stack it again so that each row is a unique combination of predictor and outcome for each occasion for each person, and you can go by predictor by outcome, and then it will spit out every combination of predictor outcome for you. So it doesn't have to be laborious if you can figure out a way to trick the program into doing more than one model at once, and stacked data is an easy way to leverage that. So once you have a sense of what matters in a bivariate, then you can combine it in whatever pattern answers your questions. There really is no way to get to the best model. That's a unicorn. It doesn't exist. Different people could attack the same data set from different directions and each settle on a different best model. The one that answers your questions is the best one, and that may be a series of models in most of these cases. So in terms of testing new fixed effects, when you are in REML, you will not be doing this via log likelihood. Each effect gets its own univariate test, a univariate wald test. If you want to test a set of fixed effects at the same time, then that is what a multivariate wald test is for. And you can do this in either REML or EML, but it's especially useful in REML because there's no analog to -2 log likelihood. And so this is the contrast statement, which is available in SAS, test in SPSS, contrast in Stata or test, and model test in M+. All software programs have a way for you to tell it, test this set of fixed effects together. So in a regression context, do you remember stepwise regression? Where you have like a box with a set of predictors and then you have another layer with a set of predictors? And on your output, hopefully you got an F value for the model at each step as well as an F value for the change in the model. That's this. That's this. That's a multivariate wald test. So it's the same principle, except that you can do this for any combination of fixed effects that makes sense. So in this example here, I will get effects of age for the intercept, age by time, and age by time squared. But if I want to phrase my question as, does age matter at all? What I'm asking is a combination of these three things together. That's a multivariate wald test that I can get by contrast, and I'll have that in my example for you. So that's the way that I would approach, does this set of predictors make the model better as a multivariate wald test if you're using REML? This can be useful, too, to decide amongst borderline cases. So if you have a higher order interaction that's marginal, you can think about, is it worth adding all the main effects that go underneath it to keep this interaction and that kind of thing. So in bold print here, the one thing you can do to screw up model comparisons is to forget in REML that you can't do -2 log likelihood difference for models of different fixed effects. That's the one thing. In terms of the letters that show up on your output, what I refer to as a wald test, some people would yell at me for using that terminology. I think the most technical definition is that a wald test uses a Z. You can call it a modified wald test if you're working within software that uses denominator degrees of freedom, such as a Satterthwaite method or Kenward-Roger, in which case the estimate divided by the standard error is called a T instead of a Z. So the difference is what critical distribution you refer it to. So if you're using denominator degrees of freedom and you're testing one fixed effect, it's going to show up as a T. If you are not, if you're assuming denominator degrees of freedom is infinite, that will show up as a Z test instead. That's what you get in M+ and in Stata by default. For multivariate wald tests, when there's more than one fixed effect being tested, numerator degrees of freedom greater than 1, T is to F as Z is to chi-square. F times numerator degrees of freedom is chi-square. So these are all very highly related. I just want you to know what to expect given what kind of estimation you've asked for. The big difference is whether or not you're using denominator degrees of freedom. And some folks had asked about methods for that. There's a little bit on this here. I use Satterthwaite in all my examples because it shows up across programs most reliably. If you have small samples, you want to use Kenward-Roger. This is available in SAS. It's not available in SPSS. It was recently added to Stata. So there's a literature on that. There's some references given for these in Chapter 5 as well. Once you get past like 20 observations or so, these really don't matter anymore, though. All right, so just wanted to touch on that briefly. Would you like to continue with our example? Why not, right? Thank you for that emphatic nod. Yes. She's like, yes, I'm here on a Saturday afternoon. I'm modeling. It is awesome. Example 3. Is this a Pepsi campus or a Coke campus? Or is that not a thing here? It's a Coke? Contraband! I am powered by Diet Mountain Dew in the afternoons. You know, Mountain Dew loves releasing new flavors. The most recent of which I saw at the grocery store was lemon lime Mountain Dew. And I said, well, then what is this? I thought that's what this was supposed to be. Has anyone tried this? Can they verify why this is not lemon lime? Because it's neon green, it better be. So I'm still trying to figure that one out. So we're working with the same data here. Response time over 6 sessions, looking to see what predicts individual differences in rates of improvement in this task. And I have 3 candidate predictors, each of which is time invariant. So this study took place over a 2-week period, so I have their age as collected at the beginning here. This is a sample of older adults, and so I've centered age such that the reference person is 80 years. I also have a measure of abstract reasoning, which is used to indicate fluid intelligence, and I centered it near the variable's mean, a score of 22 in this sample. And just for the purposes of giving you a categorical predictor, I cut up education. I would never do this in life, but I didn't have a categorical predictor that was handy, and so I made one. So I have low, medium, and high education that corresponds to high school, bachelor's level, or graduate work. And last but not least, because mixed is going to get rid of any cases that are not complete, I'm going to do it ahead of time so that my sample stays consistent across models. So this statement right here, if the number of missing is greater than 0 on these variables, then bye-bye. So the select if does the same thing in SPSS with nValid, which is the opposite of nmiss, and Stata has the same sort of logic here with the drop. So I'm doing that so that my sample stays consistent. Otherwise, people would drop in and out based on missing data, which could complicate interpretation of things. So here's my first model, 4A. I'm adding age as a predictor of each of my level 1 growth terms. So gamma 01 right here for age, that's going to be my main effect, which shows up in the code by listing the variable by itself. Gamma 11 right here in the middle is age by linear time, so that shows up next as an interaction term. And gamma 21 is age by quadratic time, which shows up last as a 3-way interaction term. So I like to think of this conceptually, the main effect of age in my head like this. It's an intercept by age interaction. This is a slope by age interaction. This is a quadratic slope by age interaction. If you think of it that way, it will always be clear what the job of age is when it's sitting there as a main effect. So age as a main effect is a level 2 effect. The latter interactions are cross-level because age is level 2 and time is level 1. At no point in this example are we going to put age or any other time invariant predictor on the random line. Level 2 people predictors cannot have random effects over people. Each person only got one value. So they can only have fixed effects. This contrast statement right here is the first time you've seen this. This is an example of how to do a multivariate wald test. This answers the question, does age matter at all? So I am lumping together the main effect of age, the interaction with time, and the interaction with quadratic time as one test. And it understands that there are to be 3 degrees of freedom for this test by my use of commas. So there's a little job security for you. Do you know what would happen if I forgot my commas? Would it still run? No, you would think it wouldn't, right? Yes, it will. It will run and give you the wrong answer. So this is what I mean by just knowing enough to be dangerous. It's very easy to be dangerous because the software is happy to do whatever you ask it to. What it would do is use 1 degree of freedom to estimate this combined fixed effect, which is not going to be accurate. So yes, commas, important. In SPSS, they turn into semicolons. Why? I don't know, just because. And in Stata, it looks like this, where you explicitly set each fixed effect to 0 within parentheses. Does the same thing using a test statement. And you can do this in model test by naming the parameters for the fixed effects and then setting them equal to 0 under the model test heading. And it will give you a chi-square for that. So the rest of these are going to be used in trying to figure out what the interaction terms are doing. So let's look at the results before we look at the rationale for those. So here's some output for you. The covariance parameter estimates. So the model for the variance is going to stay the same throughout this entire example. So I'm no longer printing R and G and Z, or R, G, and V. But this UN, that means G matrix is unstructured. 1, 1 refers to row 1, column 1. 2, 1 is row 2, column 1, off diagonal, and so on. And proc Lesa labeled these for you. So I have a line here separating the old fixed effects from the new ones. So from this point on, other than trying to figure out which variance component each of these fixed effects is supposed to reduce, the logic goes a lot like regression. You would interpret each of these fixed effects as after controlling for the other things in the model. Each of these is a slope for a 1-unit change, for the effect on Y for a 1-unit difference in the predictor. Difference versus change is something that I try to not commingle. If I'm talking about time invariant predictors, I tend to say difference, because it's not like these people are aging. We're talking about people of different ages who differ from each other. Whereas if age was time varying, then I could say change because age was actually changing within person. I think I keep the interpretation a little clearer. So the first 3 terms then now describe a reference growth curve. So we have a fixed intercept, a fixed linear slope, and a fixed quadratic slope. All 3 of these are specific to an 80-year-old because each of these is predicted by age 80. So age centered at 80 is what that variable means to me. So the pattern is less negative as time goes on. And so one easy way, relatively easy, to interpret the effects of age is to talk about what age does to each aspect of the growth curve. So if we start with the intercept is 1950 milliseconds for an 80-year-old. The intercept is also specific to session 1, given the effects of time. The effect of age as a main effect is its simple main effect specifically on the intercept at time 0. So I would say for every year older you are when you walk in the door, your predicted response time at session 1 is higher by 30 milliseconds. Older people are slower. Details at 6. Based on where that fixed effect is in my model, here's my equation. I'm interpreting this one right here, gamma O1. So which variance should that main effect of age have reduced? Yeah, you're pointing. Say it out loud. Yeah, that one. The one in its line. Age predicts the intercept. Intercept variance should be reduced to the extent that age matters. And that is down the output a ways, but to foreshadow that, yep, 10%. So yes, there's a significant effect of age on the intercept. That effect of age on the intercept accounted for 10% of all intercept differences between people. Likewise, ignoring the p-values for a moment, just to get practice in interpreting the patterns, if I think about my reference growth curve and what age does to it, There's my linear effective time, which is specific to time 0. Here's the interaction with age. So remember, there's only 4 patterns of interaction: more positive, less positive, more negative, or less negative. Which one is this? Well, this one's negative and this one's negative. This is a more negative, yeah. So the linear slope for 80-year-olds is significantly negative at time 0. For every year older than 80, that linear slope becomes more negative by 5 milliseconds. So for an 82-year-old, it would be more negative by 10 milliseconds, and so on. So older people change faster initially would be the pattern, even if it's not significant, which might sound odd until you remember that older people also were slower to begin with. So they have more room to improve. Last but not least, here's my quadratic. Here's age by quadratic. So I've got a positive quadratic for an 80-year-old and a positive interaction with age. So which one is this? More positive. So older people have a more positive quadratic, non-significant, but more positive numerically. So then I have to put that in the context of what the linear is doing. So older people change faster initially. That's this interaction term. But they level off more. They have a more positive quadratic. And it can be even more helpful than finding words to make a picture. So here's my picture. I made it in Excel. The Excel sheet I used is in your download packet. So I created predicted trajectories for a 75-year-old, an 80-year-old, and an 85-year-old. So the reference trajectory given by the model fixed effects for the intercept and time are the squares. So the vertical difference between the lines, that's the main effective age. It's age by intercept specifically. Older people are slower initially. If you were to draw a slope tangent to this line at the beginning, the slope would be slightly steeper, more negative in these older people. And the older people also have a greater bend, a more positive quadratic to counteract that more negative slope. However, as you can tell from the pictures, these lines look pretty parallel to me, don't they? Would you say? A little different, but not much to write home about? Yeah. So, not significant. So most of the story here is that older people are slower when they begin, and that age effect stays pretty much the same across time. So that's the other way to interpret an interaction term. We can talk about how age modifies the growth curve, or we can talk about how the effective age changes over time. So these estimate statements get at the latter. To figure out what the effective age would be at any session, I pull all of the effects of age from the model, and I fill in the values of time. So to figure out what the age effect is, I need at least the main effective age, so I need one of those. And then I want to know at what time the age effect is for. So for session 1, that's the one that's given to me directly by the model because that's when time zeroes out. For the rest of these, I fill in what the linear time variable would be and what the quadratic time variable would be. And so the other way to think about this is the spread. It looks like, just from the picture, that age matters less as time goes on. The lines get closer together a little bit, and these age slopes then would support that interpretation. So age bilinear and age biquadratic. Age bilinear means the effective age changes linearly over time. The extent to which the effective age changes over time as age biquadratic. So the age slope is 29 at time 1. It drops by 5 by time 2. It drops only by 4 by time 3. So it's diminishing over time, but it's at a lower rate. It's not a linear diminishment. Diminishment, is that a word? Any votes? It is now. Diminishment. But it's always significant, and the fact that these interactions are non-significant would indicate that this 29 is basically the same as this 17. Standard errors would also support that assertion. In terms of effect size for these non-significant effects, age by time would have shown up as gamma 1, 1. So therefore, it should have captured U1 variance. Likewise, age by time squared showed up as gamma 2, 1. It should have captured U2 variance, random linear and random quadratic. So here's the total effective age, the 3-degree freedom wall test. F times 3 is chi-square. The difference in the p-values is whether you're referencing an F distribution that has denominator degrees of freedom or a chi-square distribution that does not. They matter less and less. The differences are less and less the more people you have. So here's two different kinds of R-squares that I computed for you. Pseudo R-square on the bottom of the page. I'm at the top of page 16 in this example. And I labeled these two. So the main effective age captured 10% of the intercept variance. Age by time captured 2% or 3% of the time slope differences across people. And age by quadratic time captured less than 1% of the quadratic slope differences across people. These latter two effect sizes were non-significant, whereas this one was significant. So, question? Yep. This is just whether there is a simple slope for age at each session. Whether 29 is not 0. Yep. So this would be the language that folks are using in terms of interactions, probing interactions with simple slopes. That's what this is. I don't ever want to say probe because it reminds me of a very early episode of South Park. You might remember. It's just, yeah, probing is just a word that has all sorts of negative images in my head. So let's go with simple slopes. But yeah, that's what this is. There is an effective age at session 1. That's the one that's given to us by the model. But the model also predicts what that main effective age would have been at any other time. I'm just asking it to give that to me. Yes, sir. Great question. I would have a different answer depending on the nature of the variable. So I'm going to follow this policy in this example. Even though these are non-significant, I am keeping them. Because in the world of cognitive aging, you must control for age first, or no one will believe a word you say. Seriously, every field has a variable like that, where if you don't control for it, you're just done. They stop reading. So if you have a predictor that has that level of significance, you keep everything. Because in order to say that I've controlled for age, if I got rid of these terms, I could actually say that I controlled for age on the intercept. I could not say that I controlled for age on the slopes. So I'm keeping it, because I'm not getting in trouble. So I will have the one sentence at the front that says, age was included in all models, it never mattered. But it will stay there, because it never mattered as part of the story. So I'm keeping it before we get to the next one. So we have the pseudo R-squares for what each individual effective age is supposed to do. Note that the residual has not been changed. Not a coincidence. They did not change in age during the study, so it can't explain residual variance by itself. And every cross-level interaction in the model had a random slope to go with the level 1 variable, so they explained those random slopes instead. And if I want to put all of this information together into one handy number, that's total R-square. So previously, the correlation between the outcome predicted by time alone and the real outcome was 0.19, yielding a squared value of 0.04. After adding age, the correlation between the predicted outcome based on your time and I picked up another 7%. So I would say of the total variance in response time, putting it all back together again, 4% is due to changes over time, and an additional 7% is due to age. So this is a complementary piece of information that you can provide in addition to these specific effect sizes that talks sort of on the whole what contribution this variable has to the model. Other questions? So now that's an example of how I would have a covariate that I'm supposed to have. Here's something I might care about. Do smarter people improve faster on this task? So I'm adding reasoning as my measure of fluid intelligence. I'm adding it to each of my 3 equations as I did age. A main effect of reasoning predicting the intercept, reasoning predicting linear, reasoning predicting quadratic. Pick up those 3 terms then on the model line. Also asking for a combined multivariate test for the 3 terms as well. Survey says, let me draw a line here. Separate the old from the new. So my effects of age are basically unchanged in terms of their pattern. The effect of age on the intercept is diminished slightly, but it's still significant after controlling for reasoning. So part of what I was calling age is attributable to reasoning. So we do have to talk about these as unique effects, the same as in any other type of linear model. So here's my reference growth curve, which is now both for an 80-year-old and someone with sample average reasoning. The main effect of reasoning is significant, and it's negative. Smarter people do better when they walk in the door. They are faster in response time at session 1. The pattern of the interaction of reasoning with time is similar to age. Smarter people have a more negative linear slope at time 0. Smarter people have a more positive quadratic slope. However, neither of these is significant by any stretch. If this is a variable that has no special significance to anyone but me, one might argue, well, you don't need all those interaction terms. I'd say, sure. But then the question is, do I get rid of them both at the same time? So to foreshadow, let me ask you a question. Do you think that time and time squared have any collinearity? Odds are good, right? So do you think the effect of a variable multiplied by time might change if I have the same variable multiplied by time squared? Odds are good, so let's see what happens. So I'm going to get rid of just that one, the highest order term that is non-significant. So picked up another 5% of the variance in reasoning. Here's my pseudo R-squares. And this is an example of what can happen and why they're called pseudo. I got 5% of the intercept that remains after controlling for age. My slope variance went up. My quadratic variance, I got 2.4% that remains after controlling for age. And my residual bounced just a tiny little bit. So now I'm taking out reasoning as a predictor of the quadratic. This is one of the things that I do to help make things clear, but you may not necessarily need to do it in your life. I keep the spacing the same. I show the whole to show what's missing from what could be there. And for the same reason, if I don't have the effects in every single equation, I keep their numbers the same. So if reasoning shows up, it's always going to be the 2, even if there's no 1, to convey that it's the same all the way across the board. So I've dropped the quadratic term. I've added some statements to illustrate the simple effective reasoning at each session now from just linear changes in the effective reasoning over time. And lo and behold, dun da da da. So let me go back and compare side by side what it was before and what it is now. So my main effective reasoning is still significantly negative. The slope for reasoning by time has changed considerably. It's significant now. It's in the other direction. Now this is not an accident. These numbers don't mean the same thing. Because of the higher order interaction of reasoning by quadratic time, this is a lower order simple effect. This two-way interaction is specific to the third interacting variable of time being 0. So this is how reasoning modifies the time slope at time 0. Down below, in the absence of that higher order interaction, this is how reasoning modifies the time slope all the time. So if you were to create the average effective reasoning across all of these things, it would become something like this. Look at the standard error. It goes from 4 to 1. So the terms in your model that refer to the end or the beginning of time are always going to be less well estimated than the terms that refer to the middle. So if we look at the standard errors for the simple slopes, let's say from the age model here, and we go back just a second. Back one more. The simple slopes of age, right, they follow the same pattern. They're high at the beginning and they start coming down. The ends are less well estimated, so the standard errors tend to be a little higher and most concentrated towards the middle. So I wouldn't necessarily call this like a collinearity problem or anything. The model estimated these things just fine, but what it says is that we're having a hard time differentiating the linear slope from the quadratic slope in terms of how reasoning affects it. It looks like the effective reasoning changes mostly linearly over time, but it's hard to tell those two apart, whether it changes linearly or quadratically. So this is a lesson. If you're dealing with polynomials, don't kick out more than one interaction at a time. That's your take-home message. Start with the highest order one and work your way down. So if I were to look at what the effective reasoning is, staying with my new model here, what happens to the effective reasoning as time increases? Which pattern are these two numbers displaying? Negative main effect, positive interaction term with time. Less negative, very good. And that's shown right here. So the effective reasoning at session 1 is minus 32. The effective reasoning at session 2 is less negative by 2.9, less negative by 2.9, less negative by 2.9, and so on. So the effective reasoning is, if you want to put less negative into friendlier language, diminished, reduced. I wouldn't go with ameliorated because it's still kind of there. But there's lots of ways to say less negative so that people will follow you. Dig into the GRE vocabulary words that you no longer need in your brain and see if you can find some. So you can think of this interaction term here two different ways. The effect of reasoning matters less as time goes on. So these lines get a little closer together. Or smarter people decline at a lesser rate. So it's a less negative pattern of change, too. The linear time slope is reduced by 2, less negative by 2 for every unit reasoning. Yes, sir? Yep, because these are Satterthwaite. And they are calculated quantities. They're estimated by that, so they're not necessarily going to be integers. They take into account both what level the predictor is, where anything that's random is automatically level 2. So the intercept in each of these time effects are closer to level 2 degrees of freedom than level 1. But it also takes into account the relative amount of variance at level 2 versus level 1. It's based on, there's a paper from like 1946 where this started. Satterthwaite's a dude, of course, that named this method after himself, or else someone else did. And it was originally developed in the context of the t-test, dependent t-test for unequal group sizes and unequal group variances. There was an adjustment to degrees of freedom in that case that generalizes to this. In practice, I never report degrees of freedom. My table is usually estimate, standard error, and p-value, and if I get squished for space, then I resort to stars. But I don't like stars. I don't like the 1-star, 2-star, 3-star thing either. That drives me nuts. I like listing the p-values directly so that someone can stare at them if they want. Always give the standard errors, by the way. Nowadays, journals also want confidence limits on all these things. You can usually get the software to spit those out by adding a request. Like in SAS, there's a CL option that will give you confidence intervals for these things too. So, other questions? Again. It looks like I'm only chewing 3 degrees of freedom with each of these new. Yeah. So there's so there's 101 participants. There's actually only 2 predictors that are level 2. So degrees of freedom should be about 99. And that's roughly what it is across these things. Any level 1 predictor that has a random effect will have something closer to level 2 degrees of freedom. In terms of power, the power to detect any of these age effects, because what we're predicting are level 2 between-person random effects for each of these are going to be largely governed by the number of people. To a little bit extent, the number of occasions, but not nearly as much as people. So if the whole crux of your study is this, you need lots of people. If you think change is nonlinear, though, you need lots of occasions to be able to pick that up. So we're back to the answer I gave yesterday. The answer to power is always more. Power analysis involving random slopes is non-trivial. I do have some resources that I'm happy to share with you or go over how to create simulation to do power analyses, how to make up data and see what happens empirically to do a power analysis with. The tricky part in doing that is that you have to come up with an answer for every single one of these parameters in the first place. But it turns out to be not so hard if you think about interclass correlation and slope reliability. You can work your way into all of these things from there. So if you're interested in talking about that today and we have some time, I'd be happy to go over that. So I know power is a big deal. Other questions? All right, and then last but not least, this is what it would look like if you have education group. Education is a 3-group variable. So every time I talk about education, I'm actually talking about 2 different fixed effects. You need 2 terms to differentiate the 3 levels of education. And so I have these coded in the way that SAS does by default. It takes the highest group and makes it the reference. So I have 1 fixed effect for high versus low, 1 fixed effect for high versus medium. You can figure out what the missing contrast is, which is low versus medium, without recentering your groups. It's a linear combination of the existing fixed effects, and it looks like this. So the difference between medium and low in the intercept is gamma 04 minus gamma 03. Here's the math down here to prove it. How the medium group gets its intercept starts with what the intercept is for the high group plus how it differs for the medium. Same way, how the low group gets an intercept is what it is for high plus how it differs for low. The fixed intercepts cancel and you're left with this. So this is another use of an estimate statement to directly get the missing contrast. Because it's in the model. It's a linear combination of what's already there. So here's what it would look like in code to get the missing contrast. I gave you all of them so you could see the pattern, but it's a series of -1s and 1s to tell it which groups to compare and which one to leave out via the 0. So here's an example then with group. As it turns out, education does not matter. So group 3 is the reference. I get the difference between group 3 and group 2 and group 1 for the intercept, for the linear slope, for the quadratic slope. I also get a box that I haven't been printing because it's been redundant up to this point. Type 3 tests of fixed effects, your omnibus tests, that's a multivariate walled test for the 2 effects of education together in predicting the intercept, the 2 effects of education together in predicting the linear slope and the quadratic slope. And then down here, we get the specific differences between the groups, none of which is significant. Here's the means for each group at particular levels of the covariates, none of the differences in means. And so, yeah, by every standard imaginable, education group does not matter. But I wanted you to have an example of what the code would look like to do this with groups. So that's why it's here. And words. This is how I would write this up. So hopefully this can be useful to you in summarizing a series of analyses to use as a template. So, questions about that? It was that clear. I'd like to believe you, but somehow I don't. So what would you folks like to do now? We can take a break a little early. The thing that I had planned for the afternoon is cross-random effects for experimental designs that don't involve time. I also could talk a little bit about power analysis, since that seems to be a common question. Are there other topics that you might want to hear about? Sir? Time varying covariates. That is like a good month in my course. Well, I can talk a little bit about them, and I can talk about why it takes a month to go through them. So I can add that to the list. Yeah, That would make sense maybe to do that first along with power and then talk about the experimental designs. Do you guys need a break now? Would that be good? Or do you want to keep going? Someone's got to have an opinion here. Whoever talks first wins. Break. Done. All right, let's take 20 minutes and come back at 2:30.